Okay, so today section, that's not the right file. What's today?
I don't know why.
All right, yes, the correct file is for week 4. It is on Courseworks. We're going to need the manipulate package, which we used a couple weeks ago, NLEQSLV for solving nonlinear equations, and a package called run something. So if you don't have those, be sure to install them. So to start with, they're looking reasonably good. We are going to revisit the Beta Binomial, which we talked about in lecture on Tuesday. And this was one where we were able to derive the posterior distribution of an unknown probability analytically. And so just to be concrete about this, if you remember over the summer, which seems like a long time ago right now, there are all these doctors going to different African countries to try to contain the Ebola epidemic. And then some of them contracted Ebola themselves, and they got brought back to the United States to get experimental drug treatment, which one hadn't been approved by the FDA, and two, they can't make nearly enough of it right now for anyone who's not a doctor to get it anyway. So if you just sort of remember whatever your state of mind might have been in the spring of last year, to think about what would be your prior probability that this experimental Ebola drug would work in a situation like this. And in point of fact, I think 7 people received the experimental drug. So that's the N in the binomial distribution, and 7 of those people recovered subsequently. But imagine we haven't seen that data yet. It's before the Ebola outbreak, and you're just thinking about the probability of this drug, which is made by some company called MAP Biopharmaceutical, would cure someone of Ebola. And so at this point, you know, none of you are biologists, neither am I. Basically have no idea whether it would work in advance. And, you know, you might have some overall skepticism of biopharmaceutical companies and or companies that have like $1 billion of debt and are backed by, you know, venture capitalists or whatever. I mean, they certainly have an incentive to say that their product, you know, works more than it really does, but you might not have even heard any information about this company or about this drug. So you probably would, you know, if you were this time last year, you would just go with like a beta 1.1 or maybe one of the other 2 uninformative beta priors that we talked about yesterday. But suppose I told you that the MAP Pharmaceuticals published a paper in which they tried their drug on monkeys, and like, I think 2/3 of the monkeys recovered from the Ebola that had been injected into them. And so this is a situation where frequentist inference is basically not in a good place, because you have no data as of the end of, you know, a year ago. You had an extremely small amount of data subsequently, but there's no way you can put in the information that you had on the study with monkeys into your analysis. So a frequentist would say, monkeys and people are different populations. You have evidence that it works in monkeys, but that has no bearing on the probability of it working in people. Again, sort of ignoring the fact that a lot of these drugs for, awful diseases are tested on monkeys before they're tried on humans, because we know from a lot of other diseases and drugs that the monkeys have basically little versions of a human immune system, kind of. And so we know from a whole lot of other drugs that are not even related to Ebola that if it works in monkeys, there's a pretty good chance it will work in people. But Bayesian inference is the only one that really gives you a mechanism by which you can say, okay, I know something about it from the study on monkeys. I have some uncertainty as to whether the monkeys are going to be applicable to people in the case of Ebola, but we do have some information about that. And we knew analytically how to construct that posterior. You choose your beta prior multiplied by a binomial distribution. You get a beta posterior distribution, but whose shape parameters change depending on y and n minus y. So as we talked about yesterday, it's preferable to state your prior beliefs in terms of parameters that are interpretable. Actually, in this case, alpha and beta are pretty interpretable as the number of prior successes and the number of prior failures. But you can get, I think, even more interpretable if you reparameterize the beta distribution in terms of a mean mu and this concentration parameter phi, or you can think of phi as the sample size, prior sample size on which your choice for mu is based. So I think there was 16 monkeys in the study or something like that. You might want to make phi a little bit smaller than that because you have additional uncertainty as to whether the monkey is going to be comparable to a person. But you might choose mu to be 2/3 or however many of the monkeys recovered when they got this drug, and phi might be something up to 16. Doesn't even have to be an integer, but you might make it 10 to just give yourself a little bit more uncertainty about whether this is going to work with people. And then, okay, so now the summer of last year starts. We actually have, for the first time, data with humans. And we can visualize how the prior interacts with the likelihood to bring about the posterior. So we have a chunk here that basically just has a plotting function. So I'm not going to go through it in too much detail. If you just click on run current chunk, it'll pop that thing up. And mine's too small. All right, you might have to adjust your screen and run it again. Whatever. Can you see that? Can you see on yours? Okay. So in the top left, we have a beta prior based on a mu of about 2/3 and a phi of 5. So basically, counting the monkeys as 1/3 of a person. And we get a beta distribution that looks like this dotted purple curve here. If we were to increase phi, we could change the shape of that thing, etc. Phi doesn't have to be an integer, although it's easiest to interpret as a prior sample size if it is. In any event, this is a curve representing our prior beliefs about the unknown probability that the drug will cure a person. notice that if we change mu or we change phi, well, we'll get to that later. So we'll leave mu alone. In the top right, we have the likelihood curves for 8 possibilities before we've seen the data. So we know somehow that there's going to be n people who are infected with Ebola, and the probability of having y cures among those n opportunities are given by these curves here. So the black curve corresponds to the case where no one is cured. And so that reaches a probability of about 0.1 for the binomial probability mass function when the probability of cure is very close to 0. So if the probability of cure is very close to 0, we would expect to see likely 0 cures in n chances. And if the probability of cure is actually 0.9, then it would be very unlikely to observe by chance 7 people, all of whom died, even though they had a high probability of recovering. The red curve has a different shape. So that gives the probability mass function for 1 person out of 7 being cured. You can see that reaches its peak, for about probability 1/7, and gets lower if there was in fact a really large. And so you can see the other curves for different possible values of y. In point of fact, 5 people, I believe, recovered out of the 7, and so that corresponds to the purple dashed line there. And I've indicated with a vertical line where the mode of the purple curve occurs, I guess slightly bigger than 0.7. So that would be the maximum likelihood estimate of the probability of cure. Although a maximum likelihood estimate is not going to have particularly attractive properties when you only have 7 observations. Those are only have an asymptotic justification, and the maximum likelihood estimator, basically you can just include the monkeys in your sample and count them as people, or you have to completely disregard the monkeys. There's no in between. In the bottom left, we have the denominator of Bayes' theorem. What I was getting ahead of myself a little bit. So that is a constant. It doesn't depend on the probability of cure. It appears to only depend on what value of y gets realized. However, it does also depend on mu and phi. So by changing mu around, I can change, with the colors in the bottom left, how big they are. But the point of it is that this is just some constant, and it doesn't depend on p. And that's what is we know this analytically. It comes from a beta binomial distribution. It's one of the rare cases where we do have that expression, but it's just, this constant. And then on the right, bottom right, we have a comparison of the prior distribution, the posterior distribution, and the normal sampling distribution from maximum likelihood estimator. So the dotted line here is the prior, so that is the same as in the top left. The solid line is the posterior distribution from an updated beta with alpha star and beta star as its parameters. You can see the addition of 7 observations has made our posterior distribution more concentrated. But because in this case, like 5 out of 7 humans survived, and that's similar to what the survival rate was with the monkeys, it didn't change the location of our beliefs about the unknown probability very much. just reduce the variance, increase the kurtosis. And the dashed line here corresponds to the normal sampling distribution for the maximum likelihood estimator, which is again indicated by the vertical line here. And that is more dispersed than the posterior distribution. It's actually more dispersed than even the prior distribution. But moreover, the normal distribution, because it's technically defined over the entire real line, pokes out past 1. So even at 1, it has positive density here, positive area to the right of 1, even though P is a probability, it has to be between 0 and 1. So that sort of reinforces the fact that this normal sampling distribution is increasingly good as the sample size goes to infinity. It may not be good for any finite sample, particularly a small finite sample like 7 observations. So we know, even frequentists know, that true probability is not greater than 1. But they've sort of boxed themselves in and not given them any tools, really, to do anything about that, except to say, well, if I had a bigger sample size, I would have a better distribution. Yes.
So bottom left graph. So does those like horizontal lines bear any like substantive meaning? Because like it appears to me that the pink line is has the highest value, and it's related with the fact that we are most likely to have 5 out of 7 that's given this mu.
I don't think it has a particularly substantive meaning. There is a sort of quasi-Bayesian, quasi-frequentist estimator that chooses the parameters to maximize the bottom left thing. It's not a maximum likelihood estimator. It's called maximum marginal likelihood estimator. So because this depends on the hyperparameters, you know, in that case, green, you know, whatever, green would be the most likely. So it has more of a mathematical role than it does a substantive role. But we usually can't calculate it analytically anyway. So in that case, it'd be even more unlikely that you would ascribe a whole lot of substantive meaning to it. So all of these curves change as you change your prior hyperparameters, except the one in the top right, which depends on the probability of cure, but not on mu or phi. And if I didn't say it already, given mu and phi, you can map your beliefs into alpha and beta, which is what R expects to make, you know, the beta density function using the relation alpha is equal to mu times phi and beta is equal to 1 minus mu times phi. So that was good. Any questions about that? Yeah. Okay, so that was a case where we had an analytical solution. But suppose you said, you know, my probabilities are not distributed beta, they're distributed Kumara-Schwami. And this is an example, even though the Kumara-Schwami PDF is, in a sense, simpler than the beta PDF, because it doesn't involve this special function, the beta function. It's just this integral that computers know. Even though it's simpler in that respect, it makes things more complicated because we no longer have an analytical solution for the posterior distribution. So if you compile this to a PDF, it's going to be easier to read. But the kernel is going to be represented by this expression here. p to the alpha plus kernel of the posterior, p to the alpha plus y minus 1, multiplied by 1 minus p to the alpha, that whole quantity raised to the exponent beta minus 1 times the quantity 1 minus p raised to the power n minus y. And basically, anytime you have like a tower of exponents going on there, so this term involves p to the alpha, and then the whole thing is in parentheses, and then that thing is raised to the power beta minus 1. There's not going to be any analytical integral over p for that unless alpha is equal to 1 or maybe 0, something like that. In general, alpha is any positive number. And so we're not going to be able to do that integral, but we can keep going computationally. But again, we're going to have to state our prior beliefs in terms of the alpha and beta hyperparameters to the Kumara-Schwami distribution. And those two parameters are less interpretable than in the case of the beta distribution, but we can still make some progress, remembering that the inverse CDF of the Kumara-Schwami distribution is available in closed form, this expression here. And so we can plug in 0.5 for the quantile to that, and out will come the median of the Kumara-Schwami for a given alpha and beta. So if we had some idea as to what the median of our prior beliefs are, that would be a start, and we could work with that reasonably well. It's also true that if alpha and beta are greater than 1, which I didn't put a density picture up there, it corresponds to the upside down U-shaped version of it, which usually makes more sense. The mode of the Kumara-Schwami PDF, just if you take the derivative of it, set it to 0, you can find the mode of that, is equal to alpha minus 1 quantity divided by, or alpha times beta minus 1. Yeah, raised to the power of 1 over alpha. Anyway, so we have two reasonably explicit expressions for the median and the mode. And although, since those involve exponents and stuff, you're not going to be able to get an explicit solution for alpha and beta in terms of your prior median and prior mode, but it's reasonably easy to ask a computer to solve for alpha and beta as a function of your prior median and prior mode numerically. And so this is where the NLEQSLV function package comes in. It also has a function by the same name. Basically, there's only one function in that package. It takes arguments x, which is your initial guess for what alpha and beta would be in this system of two equations that we've implicitly set up in terms of the median and for a given median and a mode, and then a function, which in this case is going to return a vector of two values, and that those two values should be 0 at the numerical solution for alpha and beta. So it's basically just going to solve those equations for you. And as an exercise, you can choose a median, a prior median, and a prior mode. And there's a skeleton of some R code to get you going. So first you need to put in your initial guess for what alpha and beta would be. Those should be two numbers that are greater than 1 in order for the mode to be defined. And then basically I just set up a function called equations, whose first argument I'll call theta. It's going to be a vector of length 2. I'll just pull alpha and beta out of that. Since we're doing this, one of them in terms of the mode, which is only going to be defined if alpha and beta are greater than 1, we'll just have it return NA if that constraint is not holding. And then you do some stuff in the middle here, and then you return a vector of two things: the difference between what the equation spits out for the median and what relative to what your prior median is, and another one for what it spits out for the mode relative to what your prior mode is. And then you can call the NLEQ SLV function with those specifying your values for the prior median and the prior mode of the cure probability. So those should be numbers between 0 and 1 also. So go ahead and give that a try.
I thought why are we interested in the difference between, I thought we would just like want to be able to give it a median and a mode and have it return an alpha and a beta.
Yeah, it has to basically numerically find the alpha and beta that work, because it doesn't have symbolic capabilities, and even if it does, I don't think you could represent the expression. So basically it's going to say, okay, give me your median and mode. I'll guess alpha and beta. That's going to result in diff median and diff mode that are not going to be 0. And then I'm going to guess a different alpha and beta, and then diff median and diff mode will get closer to 0, guess again, it gets closer to 0, and then eventually it gets, as close as it can get for what a computer can hold with like 15 or 16 decimal places, and then it'll stop and say, here's the alpha, beta, and beta that are consistent with your prior median and your prior mode. So depending on what you put in for the median and the mode, there might not be any feasible alpha and beta greater than 1. And so that would suggest to you maybe you need to rethink what your prior beliefs really are. But there should be some values of median and mode, you know, around the, you know, what it would be in the monkey's case, at which there is a local solution for alpha and beta.
Yes, because no matter what you put in it, it still returns the same value.
Yeah, that should be the case.
Yeah.
Or for reasonable guesses, that should be the case. That's just the starting value at which it evaluates diff median and diff mode the first time. And then based on the derivative of, you know, the sign of diff and the derivative of it, it's going to choose a different value of alpha and beta. Yeah, so that really has no, should have no substantive bearing. But if you put in like 2 million or something like that, it might not converge to an answer.
So it's just the equivalent of like the starting values in the mode?
Yeah, pretty much. Although, yeah. So has everybody had a chance to figure out what alpha and beta corresponds to what they said? So here I've just put up a real quick picture of the Kumaraswamy quantile function. So now outputting a cure probability as a function of a quantile. And so I think I put in a median of 0.6 and a mode of 2/3 or something like that. And it corresponded to this quantile function in terms of alpha and beta. So how did I figure out what the alpha and beta were? I did this expression here. So we put in an expression for diff median, which is median minus the quantile function evaluated at 0.05, and mode, my prior value of the mode, subtract the expression that was given above for the mode, in terms of alpha and beta. So did everybody do something similar to that? Just return those things, and basically in like 6 guesses or something, in this case, it returned a solution for alpha and beta 2.28 something and 1.85. This fvec thing is the value of diff median and diff mode at the optimum. So it's like 0 to 10 decimal places. All this other stuff looks good in this case, but in general, it might tell you some warning messages. So I'm just going to pluck alpha and beta out of this thing and use them subsequently. So that's all good there. So again, the point of this is, expressing prior beliefs is never an easy thing to do. But given the choice between expressing prior beliefs about a median and a mode versus the shape parameters of a Kamara-Schwami distribution, you're going to want to do the median and the mode. If you can't do the mean, in this case, the mean of a Kamara-Schwami is not a closed form deal. Again, involves a beta function and whatnot. So we have the alpha and beta that correspond to what we think our prior beliefs are. We can now go on to draw from the prior predictive distribution, which consists of 2 steps. Draw from the prior distribution, so simulate P, and then use those P's as inputs to draw from the function given by the likelihood, which in this case is a binomial. So we're going to need a way to draw from the Kamara-Schwami prior. Again, we have the functions that we did a couple of weeks ago, the quantile function of the Kamara-Schwami distribution, and RFU, which is going to use the inverse CDF method to draw from the Kamara-Schwami distribution. Take n uniform draws from a standard normal distribution, plug those in to the inverse CDF, use your alpha and beta, and you get draws from the Kamara-Schwami. So we pipe those into R, and then using those values of alpha and beta that we had before, I'm actually going to use the more accurate ones. Whatever. Comment out. So if we wanted 1,000,000 simulations from the prior predictive distribution in a situation in which we anticipate having 7 observations that we haven't gotten data on yet. N could be any number that you want that's an integer. And then we can construct the prior predictive distribution by drawing from a binomial distribution 1,000,000 times with size equal to n and probability equal to an equivalent number of draws from the Kamara-Schwami prior distribution. So that takes like a second. And then we can look at how these draws, which are going to be integers between 0 and 7, are distributed as implied by our prior and our choice of likelihood. So there is a table of them. It gives not much probability of observing only 0 or 1 cures, but a pretty similar probability of observing anything between 2 and 7 cures. So all those have about the same probability, but the most probability is for 6, which seems reasonable in light of the prior median and mode that I specified. And all those proportions basically are going to sum up to 1. So if we wanted to use our prior predictive distribution for anything, we can create as many draws as we want for any n that we want and play around with that distribution, even though it doesn't really have a name. I mean, you could call it Kamara-Schwami binomial if you wanted, but you can write down the kernel, but can't figure out what the normalizing factor would be. So does everybody understand the prior predictive distribution? It's really a lot easier than it looks or sounds. Basically, it's similar to the bowling thing. You know, we're getting a marginal Kumara-Swamy distribution draws multiplied by a conditional distribution for the cure probability given the prior, or the binomial probability mass function for the number of successes given the prior. That gives us draws from the joint distribution of P and Y. So that's like the bivariate distribution of pins knocked down in 2 rolls of bowling. And we want to just look at the second of those 2 margins, in this case, Y tilde simulated outcomes. And we do that by effectively integrating over the first dimension, which is the Kumara-Swamy prior probabilities, leaving a marginal distribution for the simulated outcomes. But we do it with random draws rather than any analytical technique. Anna.
Specifically on the line where you're creating the Y prior, for each individual simulation, it's picking a number from the vector that's created by the prob equals sort.
Yeah, so those need to be, the length of that prob vector needs to be the same length as the number of draws that you want of Y. And for, you know, the 17th draw of Y, it's going to use the 17th draw. I sorted them for no particular reason. I mean, if I were doing something else, sometimes it's useful to have simulations in sorted order, but I don't think we're going to do any of that in this case. Okay, so we have draws from the prior predictive distribution. In this case, we'll just presume that they make sense, but in general, you could use that as a check on your prior distribution. So prior distributions are always going to involve these like abstract hyperparameter things like alpha and beta, but Y tilde is actually what you anticipate Y to look like before you observe Y. So it has a distribution of things that are observable. And so if that observable distribution doesn't look right based on what your prior beliefs are, then either, you know, you didn't specify the likelihood right, or you didn't specify the prior that really corresponds to what you think. Anna.
I think I'm confused about why we use the prior predictive distribution to check that, because I mean this incorporates uncertainty over the parameters, right? But we still, I mean, we don't know what the parameters are, but later we will make this smaller based on our updating process.
Right.
So, but that updating process is not like part of the data. I don't know, maybe that's I'm confused.
Right. So we have uncertainty about P.
Right.
Technically, we're not uncertain about alpha and beta, although in reality, we might be kind of uncertain about exactly how to express the prior information that we have in our heads. But technically speaking, we're not uncertain about alpha and beta. Those are just constants that we think we know. But we do have uncertainty about P.
Right.
And thus, our uncertainty in P drives some of the uncertainty in the prior predictive distribution for Y.
Right, but I think my question is sort of our own uncertainty about P is sort of a subjective thing that's not necessarily part of the data generating process, is it? So the data generating process should look similar to something that incorporates our limited information about P.
Yeah, I would say roughly similar. So, you know, if you made, you know, a table like this and it says, okay, the modal value is 5. Does that seem reasonable? Or, you know, 4 and 6 are about almost as likely as 5. You know, does that seem reasonable? Probably in this case, it did if you put in what I put in for prior median, prior mode. as we get into more complicated models, it's not going to be obvious at all what like the mode of the prior predictive distribution would be, given our priors on like hundreds or maybe thousands of parameters. So, you know, you can sort of at this point go back and tweak your prior if it seems as if the sort of essential features of the prior predicted distribution are not what you're anticipating the data to look like. Any other questions about the prior predictive? Okay. So if we wanted to plot the kernel of the posterior predictive, kernel of the posterior distribution for P, we can just write an R function that is the code equivalent of what we had before. We don't need to include the binomial coefficient of the binomial distribution because it's just a constant that doesn't depend on P, only depends on N and Y. So we can get that, and we can make a plot of that curve. So can't see that on the screen, but I'll make this bigger. So we get a curve like this that is in the shape of our posterior distribution. What it's missing at this point, we don't know what the denominator of Bayes' theorem is in order to divide this by some constant that depends on the data, and it depends on alpha, and it depends on beta. But so that basically just kind of tells us that these units on the vertical axis are only meaningful in relative terms. We don't know what this thing integrates to as of yet. Since it's bounded between 0 and 1, we know it's going to have a finite integral, and that integral is going to be positive, and it's just going to be some number. And then if we divided this whole picture by that number, then we would have a PDF that is non-negative and integrates to 1 over the sample space for P. And then we would have, you know, a new unnamed distribution that ostensibly we could work with. So how are we going to figure out that area if we don't have an analytical solution for the denominator? Well, in the case where there's only one unknown parameter, we can just do numerical integration using the integrate function in R. So we're going to take our kernel function. This first argument is P. We're going to integrate that from 0 to 1, which is the sample space for P. We're going to plug in the particular values of Y and N and alpha and beta that we've established. And then this area is just going to be some number, real small number in this case. And if we were to divide our kernel function by whatever is the area underneath the kernel function, then the resulting posterior PDF, which is, you know, given by this thing here, is going to integrate to 1 over the sample space of P. So this denominator thing is just a necessary evil. Well, it's not evil, necessary component in order to give us a posterior PDF that is a valid PDF that integrates to 1. So if we plot the curve of the posterior distribution that we just derived, it's in the same shape as the kernel function that we had before. It's just the units on the vertical axis are a little bit more sane, and they are the units under which that curve is going to integrate to 1. I put it in log units just so, you know, you can see better how fast it's going towards 0. But in any event, the mode of this is certainly well over here, like 0.7 something. So that is the picture of what our posterior PDF looks like. even though we can't get an analytical expression for the denominator that went into it. Question? 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 Okay. So then, if that is the function that gives our posterior distribution, how would we find out what the mean and the standard deviation of our posterior beliefs about P are?
We draw from this distribution.
Could draw from this distribution, but that's what we're going to do in the next section. How would we do it without randomness?
Like take the G function and then integrate over it numerically. Okay.
So let's do that.
Do this.
So we want to check that we do get the same thing when we do it randomly. How's everybody coming?
What should we get? Like 0.66?
Well, it depends on what you put in for your prior median and prior mode, but yeah. if you put in something similar to me.
I'm pretty sure.
Hmm?
I'm pretty sure how you did it.
Well, I was giving everybody a chance to do it by themselves.
But, can I ask a question about this function integrate?
Uh-huh.
So you cannot multiply number, some parameter by function within the function.
Right. It needs to be a
Another
function of
function.
itself. Yeah. The curve thing will take an expression. So just, a function called multiplied by something, but integrate requires the first argument to be a scalar function. So while people are still doing that, I should emphasize that this function that we've created called Posterior, because it involves this numerically integrated denominator thing in it, it's only valid for the particular alpha and beta and n and y that we've got here. So if we wanted to change our alpha and beta to correspond to somebody else's beliefs, then we'd have to go through the whole thing again to find what the new denominator is and make a new posterior function. So that is the limitation of not being able to get a symbolic expression for the posterior distribution. We're only able to say what the posterior distribution is for given values of alpha, beta, y, and n, rather than to just leave those as unspecified. Similarly, if there was another case of Ebola and someone else got the drug, then n would be 8, and we'd have either one more success or one more failure, would have to do the whole thing again. So we're still working on the integrals. Good. Anna, it's too cold to write our code quickly.
Yeah, anyway.
Okay. So if you wrote something like this, just do it in 3 lines. Basically just make a temporary function that represents g times f. Okay.
Yeah, I didn't know that you can define a function as an argument, within the function. So,
Yeah. I will do that, and you'll see our programmers do that a lot as an indication that this function is not important enough to do outside and to give it a name or anything like that. It just exists to do one thing, and then I'm not going to use it ever again. So yes, integrate the function. This is basically g of p times f of p over the sample space. And then this g function, g minus its p minus its expectation squared, that will give you the variance. And then the standard deviation is just the square root of the variance. So in a sort of analytical way, but really with a little bit of help from numerical integration routine, where it's basically just doing the little trapezoid, a whole bunch of them, thing to figure out the area underneath the g of x, f of x, or g of p, f of p curve. we can say what our posterior mean and our posterior standard deviation of the cure probability are. So then the last thing for today, we'll talk about a way that we could have done this with randomness. So suppose we didn't know about the integrate function, or we couldn't get it to work right or something like that. How would we proceed? Well, there is an R package. I don't know how you say this, R-run-neuron, that is intended to provide basically black box ways to draw from pretty much any univariate distribution. It provides actually several methods that you could read about, but I think the one that we want to focus on for pedagogical reasons is what they call polynomial interpolation of the inverse CDF method. So basically, what this is going to entail is you give it, that's a package that you need to load, and then it has a function called PIMV new, which takes these arguments. You give it either the kernel of a PDF or the kernel of a CDF, any lower bound or upper bound that the sample space might have, and a couple other arguments that we'll get to. So essentially this tells that, okay, here's a kernel of a PDF. Can you give me an inverse CDF that is basically using polynomials to approximate and try to match it up with the PDF that's given. So polynomials are easy to differentiate, they're easy to invert, and it's basically going to try to get a approximation, a very good approximation to the inverse CDF that you can't get analytically. So in doing this, it's better to pass it the logarithm of a kernel PDF. And to understand why that might make a difference, it's necessary to understand a little bit how a computer works numerically. So as I've said a couple of times, computers can't really do much beyond like 15 decimal places. And so if you pipe this thing into R, the 1 plus 10 to the negative 16th, and then test whether that is equal to 1, surprisingly enough, R tells you that that is true, even though it's false. So R doesn't evaluate these things symbolically. Basically, it just said, I don't do past the 15th decimal place. I'm just going to call that 0. So I get 1 plus 0 is 1, and 1 is equal to 1. So true. And if we were to evaluate the logarithm of 1 plus 10 to the negative 16, the thing inside the parentheses would evaluate to 1 as far as R is concerned, and the logarithm of 1 is 0, even though that's not exactly true. So that comes out as 0, and that's wrong. And if you saw earlier, we got some warnings with the curve function, and that is basically the same thing going on there. It tried to put in a value of P. It was too close to 0 when it was doing that. So any good software, R, stan, etc., is going to have another function called log 1P, and that is defined as the function log 1 plus x, but it's not actually going to do the 1 plus x because x might be too small. It's going to use a different approximation to get that logarithm if you just give it x, not 1 plus x. And x can be a negative number, so you can actually do this with numbers slightly less than 1. So if we use the log 1p function and evaluate that at x equals 10 to the negative 16th, we get back a number that's not literally 0. It's slightly positive, and it does use the relationship that, or even a better approximation to the relationship that log of 1 plus x is very close to x when x is small. So if we want to write a numerically stable version of the kernel function in logarithms, we have this thing that involves a whole bunch of products and exponents and stuff. So when we take the logarithm, by the way, when I say logarithm, I always mean natural logarithm, no base 10 or base 2 or any of that. So we define a log kernel function, which basically becomes a sum of logarithms multiplied by whatever their exponents used to be. So for this kernel, we have alpha plus y minus 1 times log p. That's going to be fine. And then we have beta minus 1 multiplied by this log 1p function evaluated at negative of p to the alpha. So if p is small and alpha is big, you could see how that might get evaluated to something less than 10 to the negative 16th pretty easily. So we use the log 1p function there. And similarly, the last term, we have n minus y that came down from the exponent times log 1p evaluated at negative p. The last term, probably, we could just use regular one. It wouldn't be so bad.
Why do we do logarithms? Why do we do logarithms for this?
It allows the thing that we're going to do next, approximating the inverse CDF, to be more smooth and numerically stable. So yeah, the exponents don't work well if you're interested in more than a few digits of accuracy. So anytime we can get rid of exponents and make them coefficients instead, we'll want to do that. So we make a log kernel function, and then we pass that to the function pinv new. It is actually going to take a function and return a function, which I will call gen. And that gen is a function that is a polynomial approximation to the inverse CDF function that corresponds to this kernel. So lower bound 0, upper bound 1. It works better if you give it a center of the distribution. So I just put in 0.5. You could have put in your prior median, whatever that was. It just helps the approximation be more accurate. And then all the other arguments that go to the log kernel function, y, n, alpha, beta, etc. We get out a function, gen, and then we can use the UR function, which stands for like random something. We pass that, the gen function that we just made for the inverse CDF, and we pass it the number of simulations that we want, and it pretty much instantly comes out with draws from P that are consistent with our log kernel. And if we wanted to make a histogram of that, we could do pretty much anything we want to with that, inclusive as an exercise that we're not going to have time to do live, but you can pause the video. What would be a central interval for which the unknown P falls within with probability 0.95? You would use the quantile function of P evaluated at probs 0.025 and 0.975. For a Bayesian, there's a 95% probability the unknown P falls between those two bounds. Rolling on, posterior predictive distribution is constructed in a very similar way to the prior predictive distribution. It's just in step 1, we're going to use draws from the posterior distribution of P, which conditions on the data, rather than in the prior predictive distribution, we just drew from the Kumara-Swamy prior, not conditional on any data. So the posterior predictive distribution is essentially the prior predictive distribution for future data that we haven't got yet. And as we can see, our posterior predictive distribution of what we anticipate y to be if n is 7 has shifted a bit relative to the prior predictive distribution as a result of the additional information that we've had by conditioning on the new information that we got last summer. So that basically gets us to the end, and the concluding point that I wanted to emphasize, basically with what we've done today, you could do Bayesian analysis as long as you only had one unknown. You could do it with numerical integration stuff. You could do it with this R-un thing to get draws from that univariate posterior distribution. So as long as you only had one unknown, you'd be ready to do Bayesian analysis. But most models in social science not going to have one unknown, may have thousands of unknowns. So it's not really feasible to do multi-dimensional numerical integration in more than a handful of dimensions. This R-un thing does have some functions to draw from multivariate distributions, but again, it only works even remotely reliably with 4 or 5 dimensions or so. Not what we're going to need. We're never going to be able to do integrals symbolically in multiple dimensions. So what we're going to learn starting next week and basically the rest of the semester are ways that are more universal ways of drawing from multivariate posterior distributions. And then we're only going to be worried about analysis of draws and not really going to do any integrals numerically or symbolically for the most part. Okay, so that is all for today.